This is the PC Trend Esbwr. PC Trend is the nuclear power plant simulator, and Esbwr is the General Electric and Hitachi developed the economic and simple BWR. It is a so-called Generation 3 BWR, completely rely on passive natural circulation cooling for the core and containment. In the middle of the mimic is the reactor vessel. It's extremely huge. For natural circulation, the height of the vessel is about 22 meters to generate the necessary gravitation head to keep the core flow in circulation. So there's no recirculation pumps either outside SBWR 2 to ABWR to 5 or the ABWR, the inside reactor vessel. So there's no pump at all. The steam is going to the turbine and condenser, and feed water going back into the vessel. Without a recirculation flow, control of the power will be difficult. So now the GE developed ESBWR rely upon the feed water temperature control to get void variation and power going up or down. See, now the simulation already start. You see it's pretty stable. The pressure of the vessel is about 70 bar or 1,000 psi, and that's similar to conventional PWR. What's different is without the recirculation flow, it relies on the so-called flux and feed water temperature control. The temperature of feed water is about 215 degrees Celsius at full power. So we are right here. In order to reduce the core power, we can heat up use higher temperature of the feed water. So that will reduce the bubble, and neutron absorption will be less, and the chain reaction of the core will be reduced. Simulation now is already in place of 1-to-1 real time. You see, let's speed it up a little, 4 times faster. You see the point, the red point, power will be going down. Originally it's 100%. That's about it's pretty large, 4,500 megawatts thermal or 1,500 megawatt electric. You see, because of the increase of the feed water temperature, our power go down from 100% down to 95% now. And the other way to control the power is by inserting the rods. For BWR, there are many control rods from the bottom. Actual control is by individual rods, but that's more for power shape adjustment. And in PC Trend, we use total reactivity or percentage of withdrawal. Suppose we insert the rods, originally 98% withdrawn. Now I dropped it to 93% insertion. You see the rods are inserted right here, okay? And power will go down. See, without changing out the feed water temperature, the power vertically reduced from 95% now down to 80%. And of course, if suppose we reduce the feed water temperature back to 215, you see the power. Right now we are still without inserting the suppose I decrease the feed water temperature, see the power will go up. So that's the idea of ESBWR for normal power operation. And for accident or transient, suppose we have a loss of offsite power. So we have no feed water supply and main steam isolation valve closed. Then the turbine trip and the reactor will shut down. See, all the control rods go in now. And this type of accident without AC powered emergency core cooling system, ESBWR used isolation condenser. That was also used in early BWR2. So the valve to the isolation condenser that's outside the containment open and condense in the pool. The condensate return to the core. So it's a continuous cooling without any coolant loss or makeup compensation. So the pool is annulus. It's actually like a donut shape, right outside the primary containment. And the pool has two systems. One is isolation condenser. The other is the passive containment cooling system. Because of the heat removal in the pool water temperature originally is the ambient temperature, something like 25 degrees. Now already go up to almost 50 degrees. Because it's in the open at ambient pressure, it's relatively easy to fill up, give additional makeup to this pool. So the reactor pressure will maintain up, now still 80 bar, although the temperature is slowly cooling down. You see the core heat right now is 100 megawatt, and the isolation condenser removal rate is also 100 megawatt. So the pressure stays at that relatively high condition. And that could last for 3 days. It's fine, it's okay. But how about if we have a kind of coolant loss? Suppose we have a steam line break. Oh, by the way, this is the malfunction list. There are all kinds of the lost coolant accident, the steam line break, the turbine trip. We already saw that. Station blackout, we already started that. So they're not mutually exclusive. We're doing that one after another now. Okay. And suppose right now we have another pipe break, supposed to be a medium size, 200 centimeters square break. I click and I close window and run it. See, there's a steam line break. We're losing 180 kilogram per second into the containment, all right, in the steam line. As a result, the containment or the primary containment dry well pressure originally is atmospheric pressure about 1 bar and now become 1.3 bar. All right. And because of the coolant steam loss, the reactor vessel pressure originally about 70 bar and now it's down to 64 bar and continues falling. So just remove the heat by the isolation condenser is not enough because we have coolant loss. So in this case, it's an aggregated accident, one after another. The Esbwr has a design of safety and relief valves. The safety reliefs are on the steam line, and it has ADS, that automated depressurization system mode. The common relief valve mode, that's when the pressure is too high, it will open. But right now the pressure goes down. So the mitigation of this is when the water level is dropped to a certain point, that in order to accelerate the cool down, we use the passive containment cooling system. Okay. So automatically, or operator can open the PCCS cooling. So the steam will go into the heat exchanger inside the pool and condense and drain into another tank called gravitation drain cooling system, and return to the vessel. Okay, so that way it decreases the pressure inside the dry well. We can see the curves, transient plot. Primary, they're alphabetical order. Pressure of the wet well, that's suppression pool, and pressure of the dry well, and pressure of the reactor dome. Click OK. Let me change the time scale to 2,400 seconds because we run now 1,800 seconds so far. Click OK. See, originally we operate at 70 bar, and because of the loss of AC power and reactor shut down, and main steam isolation valve closed, so the pressure went up. And because the relief valve open and isolation condenser cooling, it slowly go down. And at this moment, we have a loss of coolant, the steam line break, so pressure go up, go down. All right, and because we initiate the passive containment cooling system, we can continue go down, and the containment pressure, I mean the dry well and the suppression pool pressure, does not go down too much. So this is a way to control the Esbwr without recirculation loop for normal power operation, and without AC driven emergency core cooling and containment cooling in the all previous generation, BWR2 to BWR6 and ABWR. They all have active active cooling systems such as a core spray and coolant injection, etc. So this is the Esbwr, and we also keep track of the dose and the radiation distribution, isotope distribution inside the reactor coolant, the dry well, the upper dry well, and suppression pool, lower dry. This is the reactor building, and that's the turbine and condenser building, an off-site exclusive area boundary and low population zone dose distribution. So this is the newer generation Esbwr. Back in 2008 or so, the Exelon Corporation has a Victoria plant down in South Texas, a plant for Esbwr. But later on, because lack of demand and other reason, that project is canceled. And we developed, on a request of Oak Ridge National Laboratory. They support the US NRC to review the GE Hitachi's design certification. But later on, the project was canceled. So certification of Esbwr, of course, is now suspended. But our simulator PC-Tran Esbwr introduced to you the general concept of the supposedly simpler and safer boiling water reactor concept. Just give you some idea. Okay, thank you. Bye.